All right, you ready to get started? Oh, we got a lot to cover. We need a little bit more enthusiasm here. Are we ready? Yeah. Right. Okay, well, that was good enough. You know what that means? That means I'm gonna make you exercise.
What? Is that what I'm walking to?
Okay. So, what did we talk about yesterday?
Finding limits.
Finding limits, specifically how?
Using a table.
Using a table and a graph, right? Using a table and a graph. The table works. I'm not always a big table fan, but it always kind of helps you kind of get an idea of what's happening. I really like looking at it graphically. It starts to help us understand what's going on with the limit, right? Does the limit care what the value of the function is? At that point, no. Limit doesn't care what the value of the function is as long as it's approaching the same number, right? The limit has to exist from both the left and the right. So what we're going to focus on today is how do I find limits algebraically, or another way to talk about that is analytically. That's another word that you can see for it. And most of what we are going to do is using direct substitution. All right, it's fairly straightforward, right? Direct substitution. So first, we're going to start out by talking about two common limits that we see. The limit as x approaches a of some constant c is equal to c. Right? The limit of a constant as x approaches a of some c is equal to c. So if I were looking at that maybe graphically, and I have this value here at c, I know that there is some a that I am approaching along the x-axis, right? As I get closer and closer to a, the value of the function, right? As I get closer and closer to a, the limit gets closer and closer to c, both from the left and the right, correct? So the limit of a constant is always the constant. That's what that says. The limit of a constant is always a constant, that constant. Now the other one would be the limit of an identity, okay? That second one right there, the limit as x approaches a of x equals a. So that one would be our identity function here, right? Which is just x, y is equal to x. That's what we can call the identity function. So if I have some a here, and that's going to be the same value up here, right? Whatever value I put into x, it is y, correct? So that would be our identity function. So whatever value, as I take the limit as x approaches x, is equal to a, okay? And if a polynomial is either linear, quadratic, cubic, etc., then our function, then the limit as x approaches a of the function would be the function value f of a. Okay, so that's kind of the formal definition of it. Now, how do we apply these direct substitutions to a couple of examples that we're looking at here? First, we want to look at what is the limit as x approaches 8 of 11. Well, 11 is a constant, right? So the limit as x approaches some number of a constant is always the constant. So it would be 11. And if you think about that, the limit of this function right here, right? That's the function. It's a constant function. It's a horizontal line at 11. That's why it's always going to be equal to 11. Okay. Let's look at the next one. The limit as x approaches 19 of x. So as I get closer to 19 on the x-axis, what value am I getting close to on the y-axis? 19, right? So I can just think of that in terms of a slanted line. In other words, this value here, the value of A that I'm getting close and closer to from the left and the right is the limit. Okay, and then finally, notice that if I have a polynomial, according to the rule we were looking at up here, the limit of the function as I get close to A is just equal to the value of the function at A. Right, that's what that says. The limit of the function as I get close to A is equal to the value of the function at A. In other words, directly substituted in. Okay, so here for the limit of this polynomial that we have, we're just going to directly substitute 2 in for every x value that's in there. So 7 times 2 cubed plus 3 times 2 squared minus 5 times 2 plus 3. All of that adds up to be 61. Okay, if I just plug it in, add it all up, I end up with 61. All right, so that's kind of direct substitution of a polynomial. It's fairly easy and straightforward using direct substitution. So a couple of other ones that we might want to look at have to do with these. We've got what we call the limit of the power or the root. And what we're doing here is, in essence, if I take the limit of a function raised to a power, if I take the limit of a function raised to a power, then I'm going to take the limit of the function first and then raise it to the power. That's what the rule is telling me to do. So if I apply that rule here to the first example where it says the limit as x approaches 4 of this 3x minus 5 to the third power, then what that says is I can take the limit as x approaches 4 of 3x minus 5, and then I'm going to take the third, I'm going to raise it to the third power. So take the limit first is what this is saying, and then raise that value to the third power. So with using direct substitution here, right, this is a just a linear equation right here, 3x minus 5. So if I were to use direct substitution, that would look 3 times 4 minus 5. And what's that? 12 minus 5 is equal to 7. Okay, and 7 to the third power is 343. So that's an application of that property. Now, I don't have the root property listed in its general form up there, but it's the same concept where if I have a limit of some root, I can take the limit of what's underneath that square root symbol first, and then take the square root of it in this case. So this is saying, okay, the square root of the limit as x approaches -1 of 6x squared minus 4. Direct substitution is going to tell me that this is going to be 6 times -1 minus 4. And that was -1 squared. 6 times -1 squared minus 4, that would be 2, correct? And the square root of 2 just becomes the square root of 2 to leave it exactly. Okay, questions on that? Direct substitution, but we're just kind of moving around where we're taking this limit at, and it's perfectly fine. Okay, you all answer that last one for me. Take the limit as x approaches -1 of this polynomial that's raised to the 4/3 power. Okay, and what do you get? You get positive 1? Yeah, you should get positive 1. And we should have positive 1 here. So 5 times, so negative 1 to the third power is negative 1 times 5 would be negative 5. Negative 1 times a negative 1 would be positive 1, so negative 5 plus 1 would be negative 4, correct? Negative 4 plus 3 would be negative 1. The top number here tells me I'm going to raise that negative 1 to the 4th power, make it positive. The bottom number means I'm going to take the root. So the cubed root of 1 is positive 1. Okay? So remember, that's how we write from radical to rational form. The bottom number is the index, so it's not a square root, it's a cubed root, which leaves this number here as the power of whatever's underneath there. Okay. So let's kind of apply this a little bit farther to a quotient or a rational function. If we have the limit of x, as x approaches a of this polynomial function, then we can take the limit of the numerator and divide it by the limit of the denominator. That's basically what that says. Okay, it just allows us to kind of apply this property. So having said that, that's going to make this example here become the limit as x approaches 2 of x squared minus 4x plus 1 divided by the limit as x approaches 2 of 3x minus 5. So it's a polynomial, and we can just direct substitute into this. So I have 2 squared minus 4 times 2 plus 1 over 3 times 2 minus 5. Work that out, and you end up with negative 3 when I simplify that, okay? All right. This seems fairly straightforward, right? Seems very easy. Direct substitution usually is very easy, right? We know how to evaluate a function. And so we're saying that, okay, well, if I know how to do that, then I can kind of come up with our limits. Now, here's the properties that we were using above, all right? And all it's telling me is when I am thinking of these properties, which is what we were using above, I can kind of separate them out, right? So we're going to assume that the limit as x approaches a of function f of x and g of x exists. So we're assuming off the bat that those two limits exist. If they exist, then we can add the two the limits together, right? So in this first property up here, the sum property, it says if I'm taking the sum of f of x plus g of x, then I can separate them out and take the limit of the first one plus the limit of the second one. Same thing for the difference. Same thing for the product, right? If I have the limit of f times g, then I can take the limit of f times the limit of g. That's all those properties are saying. One that we use quite often is that the constant multiple. So in other words, that one I would point out. If I'm going to take the limit of some constant, some number that is being multiplied by the function, then I can take that limit, I can take the constant out, because we know the limit of a constant is always the constant itself. It's just that number. I can take that out and I just would multiply the c, right, our constant, times the limit of what we had inside of there. We've already looked at the quotient one, and then we kind of did the root one right here, and we've done the power one. All right, so those are some of the properties that we can use. You might be asked on your homework to name some of those properties. So they're fairly straightforward. We know a sum property, a difference property, right? Product, quotient, those are all math terms to be able to identify the property that's being used. But in essence, what we're going to be doing is direct substitution kind of to the whole thing. Okay, and that is fairly straightforward. Now these are in the notes that are posted, and they're also in your textbook, so you're welcome to take a screenshot of those to fill in your notes or whatever, but I'm moving on. Because the next thing that we want to talk about is, and I will point out to you, by the way, there's a set of functions that are called transcendental functions, right? Transcendental functions would be like polynomials, exponential functions, log functions, sine, all our trig functions, rational functions to an extent. These are all examples of what we call transcendental property or transcendental functions. And most of them work using direct substitution. But what we find is, what do I do when direct substitution fails? So if I can't substitute directly into the expression that I'm working with, the function that I'm working with, what am I going to do? Okay. Now, before we move on, since we have that first problem right there, the difference of two cubes. Do y'all remember how to factor the difference of the sum and difference of two cubes? So if I wrote a minus b cubed up here, what does that factor into? A binomial, right? Remember my SOAP acronym? Same, opposite, always positive. All right, so this is going to factor into a, actually, let me write this differently, sorry. It should be a cubed minus b cubed. There we go. It's going to be the cubed root of a, same, so minus the cubed root of b times a squared, opposite of what we're looking at, so plus, and then the product AB, always positive, so plus b squared, right? Same, opposite, always positive. So what would this look like then if it was a cubed plus b cubed? All right, y'all are up. You tell me. All right, a plus b, because it's the same sign. Then what? A squared minus ab, then what? Plus b squared, always positive. All right, so we have to remember how those factor, okay? So let's go down here then. When we understand, if we see that direct substitution is going to fail, we've got three things to look at. We can factor and divide, okay? That's going to be our first one. We can use the conjugate to rationalize either, this should say either, I would say the numerator or the denominator. And then we can also use the squeeze theorem, which we'll be able to look at. So those are the three choices that we're going to be using when our limit can't be found just by direct substitution. So let's look at what that looks like here. I want to find the limit as x approaches 1 of x cubed minus 1 over x minus 1. Direct substitution says I'm going to take 1 and I'm going to plug it into for x, right? What happens? Why does this fail? Zero in the denominator, that's bad. We can't have a zero in the denominator, right? Okay, so direct substitution fails. That's why it fails. It caused us to get a zero in the denominator, which is undefined. So instead, we want to see, okay, let's try to factor this. I'm looking at the denominator and I've got a binomial down there, right? So I'm hoping that I can factor the numerator into something that is similar to the denominator. That's the goal. So I'm going to take the limit as x approaches 1, and I'm going to factor x cubed minus 1. That's why we just looked at this. So the cubed root of x cubed is x minus the cube root of 1 is 1 times x squared plus x plus 1 all over x minus 1, right? That is our factoring of the difference of cubes there. Now I can cancel the x minus 1 factors because they are common. This leaves me then with the limit as x minus 1 of x squared plus x plus 1. And I can use direct substitution on that. 1 plus 1 plus 1 gives me 3. So the limit of that function is actually 3. And I can find it algebraically. Think about what happened to this function. Y'all recognize what that function is, right? That the function we started with, what would it be considered? A rational function, right? And when we canceled that common factor, what did we end up with? A whole, right? A whole. Remember, that's going to give us a whole. If we were to graph that on our Desmos or a graphing calculator, you really wouldn't see that whole, right? Most of the time, we don't see that whole. So what we're doing here is, remember, we're not really concerned what's happening at the whole. I just want to know what's happening as I get close to the whole. So what we've done is we have created, right, a polynomial that would be similar to the rational function we were just doing, right? Except it doesn't have a whole. And I can directly substitute into it because I'm not concerned at the whole. I'm only concerned with what's happening around the whole. So in essence, we are creating and taking the limit of something that is similar to what we had, but we can do it now algebraically. All right, let's up your algebra skills here. Here I have the limit as x approaches 0 of 1 minus e to the negative x over e to the x minus 1. So if I direct substitute into there, what's e to the 0? Anything to the 0th power is going to be 1. That causes the denominator to become 0, excuse me. So direct substitution does not work here, right? Okay. So let's look at this. I've got a negative exponent in the top, right, in the numerator. Let's take this and let's rewrite this. The limit as x approaches 0 of 1 minus 1 over e to the x divided by e to the x minus 1. Now, I don't like that e to the x in the numerator, right? Because it's a fraction. So if I multiply top and bottom to get rid of that e to the x, then that's going to give me the limit as x approaches 0 of e to the x minus 1 all over e to the x minus 1 times the e to the x I already had. I'm going to leave it factored. Okay, I'm not going to distribute here because I'm kind of trying to cancel some things out. Are we good with what I did right there? What happened? What did that create for me? It cancels the e to the x minus 1, correct? doesn't that just give me 0? The limit, what is e to the 0? E to the 0 is 1, right? That's why, okay. Had a little brain moment there, right? So this gives me the limit as x approaches 0 of 1 over e to the x. Direct substitution would be 1 over 1. So the answer is 1, right? E to the x would be, e to the 0 is 1 is what I should say. So it kind of took care of that for me, didn't it? Yeah? Yeah. Okay. So maybe you all need to practice this one right here. You think you can do this one? This is all about factoring. How many terms do I have in the numerator? 2 terms, okay? The second term is a perfect cube, correct? The first term is also a cube, right? E to the 3, yeah? Okay. So could you factor that just like we did before? The cubed root of e to the 3x. What was the cubed root of x cubed? It was just x, right? Okay, so the cubed root of e to the 3x has to just be e to the x, breaking it down into its most basic form. Write it down. Let's just see if you can factor this. Can you factor it into that? How many of y'all have that? Yes? Mhm. Okay, everybody come up with that factorization? That's all I want to know yet. Speak. Yes?
Yes.
Okay, you see how we factored the denominator? Second term is a perfect square, the first term is still, we can separate that as well. Okay, because I can cancel those things now, right? So I'm taking now the limit as x approaches the natural log of 2 of e to the 2x plus 2e to the x plus 4 all over e to the x plus 2. Now let's do some direct substitution in there, right? So I would have e to the 2 times ln 2 plus 2e to the ln 2 plus 4 all over e to the ln 2 plus 2. All I did was throw in the ln 2. Everywhere there's an x, correct? What is e to the ln? They cancel, right? It becomes 1. Okay, so then those cancel right there. This is actually, this 2 in the front, y'all look up here really fast. That 2 up front, kind of picture it being up here in this second position, right? So this is gonna actually become 2 squared, right? That 2 right there from the power rule comes up to the top, all right? So this really becomes 2 squared plus, this is 1 times the 2 I already had, plus 4 in the numerator, right? Because ln 2, right? Actually, that would be 2 times 2, I beg your pardon. That'd be 2. 2 times the 2 I had, plus the 4, all over 2 plus 2. So I would have 12 over 4 or 3 using direct substitution. Yeah? Okay, so all of a sudden we use some of what we were using in college in pre-calculus a couple of weeks ago, right? Okay, that's why we kind of went over it. Now, this is an example of when we're using factoring, right? It didn't start out as just some simple little trinomial we were trying to factor and solve. That's what we worked on first, but you can see how maybe we need to do a little bit more with our polynomial, our rational, in order to turn it into something that I can then cancel, okay, or factor. Now, the next idea is, okay, well, perhaps instead of a factoring idea, maybe I want to multiply by the conjugate to rationalize either the numerator or, I'm going to put this, or the denominator. Either way, you're rationalizing it. Remember, that's when we multiply through to get rid of the radical, isn't it? Okay? So here I have the limit as x approaches 0 of this function. And we know that if we did direct substitution, you're going to automatically have a 0 in the denominator. That doesn't work. Okay? Doesn't look like I can factor this very easily. So instead, let's start by multiplying by the conjugate. So where is the radical? In the numerator or the denominator? In the numerator. So we're going to multiply top and bottom by the square root of x plus 1 plus 1, all over that same thing. Because that's the conjugate of the numerator, right? Same function, difference of signs. So we end up with the limit as x approaches 0. Now remember, the goal of multiplying by the conjugate has to do with the fact that I'm going to take these two binomials and I'm going to square the first term and then I'm going to subtract the square of the last term. That's all it is, right? That's why we multiply by a conjugate. It's the square of the first term minus the square of the last term. The first term here is the square root of x plus 1. Squared becomes what? So x plus 1. And the square of the last term is just 1. So it becomes x plus 1 minus 1, and leave the denominator in its factored form. Don't expand this, right? Let's just leave it as x times the square root of x plus 1 minus 1. It may be that you have to actually expand it and simplify it at some point, but I don't really want to right now. Yeah? Plus 1. Thank you. Okay? All right. The numerator. What does the numerator simplify to be? The limit as x approaches 0 now of just x over x times that denominator plus 1 plus 1. Okay, and so our x's cancel. That leaves me with a 1 in the numerator, right? There is a number up there. It's 1 over the denominator, and I can use direct substitution. So this becomes 1 over 0 plus 1 under the radical plus 1, or in other words, 1/2. It's okay to have that radical in the denominator when I'm using the direct substitution. Okay, let's try that again on the next one. Same concept. Right? So we're going to multiply top and bottom by what? 4 plus the square root of x? Yep. So the limit as x approaches 16. And when I multiply that numerator, I get the first term squared minus the last term squared, all over x minus 16 times that. Now, what's the difference between the numerator and the denominator at this point? The factor. So if I were to rewrite this as, if I multiply through here, let's say by a -1, then I could rewrite this as -1 times x minus 16, all over the x minus 16 I had. The only difference between those is the signs was different, right? So factor out a -1, in other words. That makes them the same, but I'm leaving my -1 up there. This is still the limit as x approaches 16. But I can cancel those common factors now because they are now the same. So direct substitution works, doesn't it? At this point, if I directly substitute in 4x, I'm going to get -1 over 4 plus the square root of 16, or -1 over 8. Okay? So factoring, multiplying by the conjugate. Now, it doesn't have to be that the rational is only in the numerator. You could have a problem that we're going to work on your classwork where the radical is in the denominator. It's the point that you're trying to get rid of that. All right. Let's look at this problem right here. It's kind of an extension of that. It says, I want to know what the limit is as h approaches 0 of this function, f of x plus h minus f of x over h. That's kind of the groundwork we're laying for it, but I'm going to let my function be equal to x squared, and I'm going to let x be equal to -2. So if the function is x squared, then f of x plus h has to be x plus h squared, correct? Yeah, it's just the function x squared, but now we're talking about x plus h instead. So in the numerator here, I am going to figure out, all right, well, what is x plus h? What is f of x plus h when I plug in a -2? If I let x be -2, this is going to look like -2 plus h squared. That represents f of x plus h, minus -2 squared. That represents my x squared part, correct? All over the h that I have. And I want to know what's the limit as h approaches infinity or 0. Well, let's clean the numerator up, because at this point, if I just do direct substitution, will that work? Can I directly substitute into this and take the limit as h approaches 0?
No.
Why?
Because the h is the bottom.
Because h is in the bottom. Okay. All right, so let's look at the numerator. Remember, this is a binomial. Square the first, double the product, square the last. So if I square the first, I'm going to get 4. If I double the product is -2h times 2 would be -4h. Square the last, I get h squared. Minus -2 squared, which is 4, all over h, and I am still taking the limit there. Okay, let's clean up that numerator a little bit more. What do you see? The 4s are going to cancel, correct? Can I factor the numerator also?
Yeah.
What do I get, Isaiah?
4h plus h.
So the limit as h approaches 0 of
-4.
h times -4 plus h all over h, correct? Because I can factor an h as a GCF out of the numerator. That allows me to cancel the h's. Because I can cancel common factors there. So direct substitution is now going to work. So this becomes -4 plus 0, which is just -4. Okay? We will come back and visit this exact setup, f of x plus h minus f of x over h, taking the limit as h approaches 0, Monday. A lot, okay? That's actually the derivative at a point. Okay. Questions on that so far? A lot of algebra, isn't there? We're not really doing anything except taking the limit and then working with a whole bunch of algebra. Any questions on that? Okay. So the next option we had, if taking the limit fails, right, if direct substitution fails, the next option we have is to use something called the squeeze theorem. Now, the squeeze theorem just basically says, if I have this blue function f of x, and I have this function h of x, and g is sandwiched in between the two, right? So if I have g, which is in between h and f, if I take the limit of f, and I take the limit of h, and they are the same number, then g has to have the same limit, right? So if the limit of this is 2 and the limit of h is 2, then the function in between also has to have the same limit. We're approaching the same number. All right, it's called the squeeze theorem. It's also called the sandwich theorem. So if you're thinking about taking the limit of these two endpoints and you get the same value, then the number that's in between them must also have the same limit. Logically, it makes sense. Okay. So let's take this idea here. Let's say that I want to prove that the limit of, as x approaches 0, of x sine x is in fact 0. All right, and I want to show this using the squeeze theorem. Well, if I started out thinking about sine x, right? Because I've got to be able to, if I'm doing the squeeze theorem, I've got to be able to put this in between. I'm going to put this function in between two boundaries. So we know that sine x is bounded on the left and the right, right? The output values for sine x are going to be between negative and positive 1, correct? Okay. So if I were looking at this and I said, okay, sine x is less than or equal to 1, greater than or equal to negative 1. We know that to be the case. If I multiply every term here in this inequality by x, I end up with negative x must be less than or equal to the x sine x I'm trying to prove, but that's also less than x. Just algebraically working that, right? Do you agree with that so far? So if I were to come in here then and say the limit, and I want to take the limit now as x approaches 0 of negative x. What is that equal to? What?
0.
0. And the limit as x approaches 0 of positive x, well, that has to be what? 0. So if the limit on the left side is 0 and the limit on the right side is 0, then the limit of the function in the middle is squeezed, right? It has to also be the limit then as x approaches 0 of x sine x must also be 0 by the squeeze theorem. Okay? That's what the squeeze theorem allows us to do. Take the ends, take the limit of the two ends, and as long as they're the same, then whatever was in between must also have the same limit. Okay, intuitively that makes sense. Now, we're not going to go into this proof, but you are going to go into it as an activity later on. And you can actually do that squeeze theorem proof to be able to prove that the limit, so you need to memorize these. Put a star around whatever you're looking at, and you better memorize these, all right? Because the limit as x approaches 0 of sine x over x is going to be equal to 1. Direct substitution does not allow that, right? If I just directly substitute in a 0, I have an issue because I've got 0 in the denominator. But you can prove using the squeeze theorem why the limit is equal to 1. And I'm going to leave those two theorems, those two proofs for you outside of class. So these are our three special limits. Most of the work we're going to be dealing with is going to be dealing with that first limit of sine. But if you find a structure that looks similar to this, we are going to be able to take the limits that we know and apply them. So the first limit example we're going to look at says, I want to take the limit as x approaches 0 of tan x over x. Direct substitution fails here, doesn't it? Yep, 0 in the denominator means I have an issue. So that trigonometry identities that Jonathan loves so much is going to come back and rear its head right here, okay? So the limit as x approaches 0 of 1 over, let's see, let's write it this way. Can I rewrite tangent in terms of sine and cosine? All right, so let's rewrite this as sine x over cosine x times the 1 over x I still had, correct? Yeah? Now, can I want this right here. I want a sine over x, sine x over x. And I can rewrite this by saying the limit as x approaches 0 of sine x over x times 1 over cosine x. Now I could use the product property of limits and be able to say, okay, the limit of sine x times the limit of 1 over cosine x, or I can just take the limit in between here. Hold on, I'm going to show you. This becomes, what do we know the limit of, as x approaches 0 of sine x over x is? 1. Okay, so that becomes 1. And can we use direct substitution here? What is the cosine of 0? Trig will not leave us. 1, right? So this becomes 1 over 1. Cosine of 0 is 1. So now the answer is 1. So we did a little bit of a rearrangement there, didn't we? Before I move on, questions on this? Where's that 1 over cosine? All right, so this is what so tan x becomes sine over cosine. And I wanted to just, so I still have a 1 over x that I pulled out here. But I want to put this in the form of my limit that I have up there. right? That limits sine x over x. So I rearranged product, right? Because I can just rearrange those because they're just multiplying. And I rewrote it then as sine x over x times the 1 over cosine that I still had, okay? Sine x over cosine x. If I take the limit as x approaches 0 of sine x over x, I should say, is 1. That's what the property tells us above, or the limit. And the limit as x approaches 0 of 1 over cosine x using direct substitution, right? The cosine of 0 is 1. So 1 over 1 is 1. Isaiah, did that answer your question? Did you have a question?
No, it's good.
You don't know yet?
Yeah.
Yulissa? Just, all right. Let's look at another one then. Okay. Okay. As a side note, our special limit that we were dealing with up there says that if I take the limit as x approaches 0 of sine of, we'll call it any x, any n x, over that same nx is equal to 1. In other words, whatever value I have in that argument position, right, has to be the same value in the denominator. That's what that says, okay? So whatever is here, that 3x, I would also need to have a 3x in the denominator to apply this limit, all right? That's what we want. We don't exactly have that in this particular case. I need, right, I want a 3 here, don't I? I want a 3 down there in the denominator. So let's see if we can do a little magic. So we're going to say, okay, the limit as x approaches 0 of, if I need a 3 in the denominator, we'll just write it like that so far. And if I have a 3 that I want in the denominator without actually changing anything, we can always multiply by 1, right? So I would also have to have a 3 in the numerator here. Because 3 over 3 is still 1 times the sine of 3x over x that we had. Now let's rewrite this. This becomes the limit as x approaches 0 of, I'm going to write it as sine 3x over the 3x times the 3 that we still have. So where did all these things go? This 3 that's the numerator here is actually that 3 that's right there, right? Yeah, you see that? Yes. And that's a constant, isn't it? 3 is a constant here, right? So we can take the 3 out, because wasn't that the property I was telling you where you're multiplying a constant times the limit? So we would have 3 times the limit as x approaches 0 of sine 3x over 3x. I just pulled the 3 out because it was a constant. What is the limit as x approaches 0 of sine 3x over 3x? It's 1. The limit of that portion is 1.
Suppose the x's are the same, or they have the same coefficients. So it would be
Yes. So we would have the 3 that's still in front times 1, end up having 3. Okay? All right. So we're going to do 12:30 practicing these problems. All right? Then we have another, then we're gonna start talking about continuity. And then I just rearranged it, right? So I just took this denominator and moved it over here. Yeah, because technically it would be what, sine times 1 or cosine times x.
Yeah.
So I just separated it back out to look like I wanted it to look. Multiplication is commutative, isn't it?
Yeah.
Order doesn't matter. So if I'm sticking with just the order of the denominator, I can rewrite the denominator any way I want. And I can rewrite the numerator any way I want. Because it was still. Because I was trying to set it up so that I could then rewrite sine over x, which would give me the property I wanted, and then I have left over 1. You don't have to separate it that way. It's just easier for me to see it. All right, check your answers with your neighbor. Check your answers with me, but we're gonna only spend about 20 minutes working on this. Always try direct substitution. Right, that's the easiest method. Always try direct substitution. Those of you that are sitting at your desks all by yourself, lean over and impart your wisdom to the other people.
Yeah.
And if you have a question, ask. Did you know there are many campuses that don't allow you to use a calculator? 27 or 3, right? 3 times 3 is 9. 27. Mental math, to get away from it, we should actually practice it a little more. Right, you get a sheet work. Yes. your other stuff, right?
Doesn't double check work. Doesn't help.
Wait, you did. Wait, they were 14.
E.
Perfect.
I look at the next problem.
That's right. Always try and write substitution first. That was the easiest. That first.
So what you're saying is making do pi times 7.
So 7 pi over 6.
7 pi over 6.
Yeah, which is secant is.
Yeah.
Yeah, that's right. It was, it should be, you didn't add that right.
Raise square root through negative 1.
Right.
So this, that's.
Is it?
Oh, yeah. Two.
We're in the, what, third quadrant?
You keep it negative.
Yeah.
After you flip it, right, so it'd be negative 2 over square root 3, which is 2 negative 2 negative 2. Yes.
So that's cosine.
My
Yeah. She said, but it's.
I also.
Yeah. So.
Yeah.
Sine.
Oh, wait, no.
Wait, sine. Pi 0
Well, sine pi is, sine pi would be 0, right? So
Times
0 times
0.
0, 0.
So the e to the negative x.
1, right?
Or e to the negative 6.
1. It's just 1, yeah. So it'd be 0.
Hey.
I was-
So this is 0 over 2. Right.
Yeah. So it'd be 1, what's that? Well, not yet, because it's not. It's not. This one.
Or you could just.
X over E X.
Because G is one.
So just
Negative
one.
So the inside of it. But I bet.
Don't think that.
Yeah.
See, you're not.
So.
Just.
No.
Yeah, that's right.
Or.
Yeah.
No, 'cause when you click them in.
That bottom one.
Let me know if you get 1 or 0.
Negative
Right.
one.
And then you have the rest.
Corey, if you don't get it.
This is my favorite thing.
Gosh. L of E is just one. So it's just,
Exactly.
What's the natural law of one?
Yeah, you know whatever.
That's exactly how. I did it differently.
No.
I wrote this as natural law of E to the negative one. Natural law of E to the negative one. Those two cancel.
oh,
So I got negative. I always forget that the natural law of
Oh.
one.
yeah.
So you rewrote it?
No.
You rewrote it.
I wrote it as that. These two cancel.
Yeah.
And I know that that is it.
So then the answer is like, see, I told you it was negative one.
But Isaiah and Nicholas were doing it a little bit different. They broke it up into the.
Sorry, is it negative 1 or 0?
Negative one.
Yeah.
All right. Good.
So this is ship 1 over E, right?
So what's just L and E is times E.
So L of E is negative 1.
Yeah, okay, so whenever you bring in the one, it would be
So
over EX.
Or do you have this?
So you can just make it a negative.
You leave that into L of E.
And then that cancels out.
Negative 1.
Yeah.
Yeah.
So flip it and you would have square root of 3 in the denominator, right?
So what's the negative?
Negative 1.
Is it 46? Limit as X approaches 3X.
Just try direct substitution. Always try direct substitution.
So what if we know?
If that ever direct substitution does not work, so it fails, that's when you go to special. Like, yeah, is that? Yeah. Did you think that you could cancel that natural log with that? You can't do that because it's inside of the argument. You have to like perform your, the way I look at this is I use my exponentials first. Or actually I did direct substitution first. This would be the natural log of 1.
Well, I mean, if this is supposed to
And
cancel
so I rewrote
on the other.
the x as even the
X
negative
plus 2
x,
is cancel. So you got the 3X plus
right?
1.
So now do the natural log of even the negative x,
So negative 0.
right? And the natural the natural log of P of those are going to cancel. Right here, it's hiding the inside of the argument. It's not one. Direct sense.
Think about here, when we did logs. we had certain rules for-
Yes.
Dx plus one.
You can't just factor it out.
And then isn't e to the 0?
E to the 0, but. Yeah, E to the 0.
1 minus 1 is 0.
Yeah, no, the answer is 2x. Dx plus 1, dx minus 1. Oh, right, no, it's 1. The answer is
Oh, wait, 1 plus 1, so it's 2.
2. Why can't we do this?
Make them smiley faces. Make them witches happy, right? You can.
Yeah.
It's just an algebraic concept.
Oh,
Make
what
them
is this? Why is there a triangle in front of X?
Delta X.
Yeah,
What's that even?
Eric Parts.
She took forever.
I gotta get all like statisticians.
Let's try this. Yeah, because it's very hard.
Delta X.
Have the outlines of it. So we didn't have the right place. This one's for the X.
Over. Alright, that's X.
So replace the funny delta and something else.
Because it's really just a symbol. You can make it a smiley face. It makes you.
So it doesn't.
Because we can add we just did something.
We can do this. Yes, X is it's not X.
Where's that?
Might just make it Y, honestly.
Yeah. The squeeze here. No, it was. Yeah, times X is H1 instead of X. So X plus H. Although I didn't know.
Okay.
So then you get.
Well, no.
Literally the same.
Yes, it's the structure.
So, okay, so we'll continue. 4. Yeah, so we're gonna have that. X squared.
Stuck?
Delta X squared. Or plus delta X. Plus, X delta X.
All right, you got about 7 more minutes.
Or no, it'd be X plus X delta X. Oh,
Yeah. Really like.
Oh, you said 40 direct substitution, right? So once direct substitution.
right, so it's negative
You
2.
do that.
Squared, and she has a negative 64.
And then see if there's.
Or
I didn't finish
plus
64.
2. R minus 4H.
Yes, you could have.
Maybe like that. So we just, so we need H zero.
Correct.
Yeah.
Right. Right, so you're gonna try that at first. Now, the next thing you're gonna try is factoring,
Four minus.
and you're gonna see if this should be a clue. Can I
So
factor
square the
this
first.
so that x plus
Square the
2
first,
is a
and
factor?
multiply
That gives you
multiply the two
the route to
together.
go on.
Yeah.
Is that what you want?
Double. So it's 2x. Oh, you're reading through the bar.
Yeah, well, I
Yeah,
do
you just
x
make it
substitute,
H.
right?
Here's the
And
row.
then, yeah. Now, I've seen it, Isaiah,
Turns
it
out like
was
that.
there, a little bit, Isaiah actually from here.
Plus.
You wrote the natural log of 1 minus the natural log of 8. And it gets.
Yeah.
Yeah, but
Double-
you gotta play
Double
this
the
on.
product.
Okay. What she
Did
did.
you question answer?
Oh, she put in the.
So then, the x squared and squared. Right?
Yeah, so.
Well, now you can change the next.
Wait, what? Oh, okay, yeah, yeah. Yeah, so.
Let's see if this works. Back up.
Yeah, we can. So, X.
The factor? So you only have, so you need this to be.
So you
x
got,
plus 2.
so then there's nothing X.
X plus delta.
So you would check just to make sure, so this is gonna be +6 minus 1 is
So. X. Yeah.
square the first. So x squared is 2x. Right? So it'd be 2x plus delta
Yeah,
x
substitute the zero. So.
for delta x.
So it's 0.
No.
Oh.
Only
So
delta x.
it's 2x plus 0.
So it'd just be 2.
Just x.
Okay.
I see that.
X squared.
Yeah.
I'm glad I have examples.
Huh, I was thinking about it, you know, spreading it over, separating it.
That's what I was staring at for a while. Finish.
Yeah. I tried turning it.
Take 1 over x away.
Just so you know.
1 over x is the opposite. Pull 1 over x out and rewrite tan squared as sine squared over cosine squared. Yep.
1 minus cosine x over x.
Maybe.
No.
See if that works.
What do you mean? Oh, it's 0.
0.
Because wouldn't you now have, go through it, so keep going. This is what I wrote. They're all being multiplied, right?
Yeah.
Could you not also have sine x over x times sine x? Maybe, because that's really just repeated multiplication, right? Thinking through this and when talking, you don't remember that. That seems like it would work.
Oh.
See, he's.
But the other one earlier was just to prove that match.
Yes, yes. Okay, what do you want to have here? What do we want?
Oh, sine squared, yeah, okay. Sine x over x.
Yeah,
But you would have to square this x.
no, we don't want that.
So,
Could I not also write that as sine x over x and another sine x in the numerator?
which one?
Isn't sine squared x the same thing as a sine x times a sine x?
Oh, yeah. Okay. So then. Sine x.
You end up with. Leaving you with 2x plus delta x. No.
Okay, now we could multiply times the.
So sine x
Then
over
it
cos.
factors.
Multiply by the con, changing your wording.
All right, look up here, check your answers. I'm fixing to move this along. I have 42 up here as well. Even though I put your 42 at the bottom. Because I'm fixing to move on and we're gonna do continuity in just a second, okay? So these are questions 30 through 36, and then it picks up again 46 and 50, I think is that number. 42 is mixed in here. You haven't already checked these? Okay. You ready for me to move it?
Yeah.
Okay. 54, 58. I reworked 58 in blue. I liked that better, which is the way I explained it to you in class today. 54 is negative 110. 58 is 1/4. 64 is 2x. Is that what you were getting, Jalen? $68 is 3 and 72 is 0. Okay? Write down those answers and then come back and ask about it, okay? Write down those answers. See if you can work them out.
Yeah. Wait. Why is that split like that?
Which one?
0.72.
Sine x split. Oh, it does sine x.
Okay, so you
What, man?
you just had to stuff.
So if it's sine x squared, sine squared x times 1, then it's the same thing.
Anytime I write something in exponential form, isn't that just repeated multiplication?
Yeah.
So I can just separate it. So sine squared x is the same thing as sine x times sine x.
Yeah.
Okay? So you're practicing on these. You're kind of getting a feel for how this is going. This is a fairly long lesson, I would think, in your homework, all right? The quiz that I'm gonna give you on Friday is gonna cover Thursday, yeah. The quiz I'm gonna give you on Thursday is gonna cover what we did yesterday, what we do, and what we're doing today. So I would encourage you to get in and practice the homework over those two sections and ask me any questions tomorrow. Get in and try to get as much of it done as you can. Ask questions tomorrow because the quiz will be on Thursday. All right? Okay. So Now we're going to talk about continuity. What we did with finding the limits graphically and from a table, and then algebraically are all great, as long as our function, in fact, the limit was easy to find when the limit existed, right? We saw that we have some problems whenever the limit doesn't exist, okay? And so what we're going to talk about in this part, when we're thinking about continuity, is what's kind of, it's easy to take the limit if a function is continuous, like a polynomial that has no breaks. But we need to kind of talk about what do we call functions that have those holes in them, that have those asymptotes in them, because they are not continuous. All right. The easiest way to talk about continuity and to determine whether a function is continuous is if I were to trace my finger along this graph or my pencil along this graph, in order for me to get to each of the values, would I have to skip over it, right? So if I start here, there's an open hole on the left-hand side, which means that the function actually starts just to the right of it, correct? It doesn't exist at 0, 3, but it does exist as we move forward. All right, so if I'm tracing here, I have another hole, don't I? So I would have to technically pick my pencil up and jump over it, wouldn't I?
Yeah.
Or hop over it. I can come down here and I have a hole, but it does exist here, but I would have to move my pencil to get up there to actually, you know, put my pencil on everything that was continuous where I drew it, right? So if I'm going along here, it's going to jump down here to this piece of the puzzle, right? And then as I move this way, we have an asymptote that's occurring. So I'm going to have to pick my pencil up, right? So it's this idea that if I don't have to pick my pencil up at all in this entire function, it's continuous, okay? If I have to pick it up because I've had a hole or I have some sort of asymptote, then it's not continuous, and we call that discontinuous. All right, so if we're looking at this, this is kind of our example that we're going off of. Now, we have some things in this that I just kind of want to explain as we move a little bit further down here. We know that we have this asymptote here, right? So we are not continuous there. If I were taking the limit, if I was taking the limit of this function as the function approached 5 from the left, then the limit is actually going where? Right. So it's unbounded, right? So, and if I come at the limit of this function from the right-hand side, it's doing the same thing, isn't it? It's also unbounded. So does the limit exist here at 5?
No.
Okay, that's kind of an important concept we're going to talk about too. Over here, right, we know that this is not continuous because I have to pick up my pencil, but what we have here is a discontinuity, right? Because again, if I take the limit, let's talk about that point at 3 when x is equal to 3. If I come at the limit as x approaches 3 from the left, the limit is actually 2, isn't it? Okay. And as x approaches 3 from the right, the limit of that function is. So again, the limit doesn't exist there, does it? Okay. All right. This is kind of what we're talking about here. So there is this idea, this checklist, if you will, all right, for continuity. Okay. And then I remember I changed these, I edited these. Is this the same box? It's close. The definitions are going to be exactly the same. I just like the way this said it, but this is better. It's the same thing. So in order for us to have continuity, we have this checklist we need to go through. So in order for f, the function, to be continuous at a point A, the following 3 conditions must be met. First of all, A, right, must be defined, or f of A, I should say, must be defined. In other words, my A value has to be in the domain. The second thing, the limit at A of the function must exist. So The A has to be in the domain. In other words, the function is defined at A. The limit must exist at A. And the value of the function at A is equal to the limit of the function at A. So those two prior things must just be equal to each other. Those three criteria have to be met for us to be able to say that it's continuous at the point. And most often when we're thinking about discontinuities or things being not continuous, we have these holes. We can have what we call a hole or a removable hole. And I'll make clear what that is in just a second. Or we have some sort of jump where I'm going like on a piecewise function or asymptotes. Okay, so let's look at just 4 examples down here and we'll see if we can discuss their continuity or discontinuity. So let me just give you all a hint. There's a lot of graphs and there's a lot of rules that we end up putting in this. So I'm encouraging you to print the notes and bring them with you so you don't have to, or leave a space and go back and cut the notes up, copy and, cut and paste, some scissors and glue, right? That's another way to do it. Leave yourself a little blank spot, all right? So we can move on quicker, okay? Or take a picture, right? Everybody has a cell phone, take a picture. So let's look at this one here. I want to discuss the continuity of the function, in other words. Would we describe this as continuous or not? This is discontinuous, and why?
Because that's an asymptote.
That's right, it's discontinuous because it has a asymptote, or another way you may see this, depending on which book we happen to be looking at, it has an asymptote at x is equal to 0. Another way to describe that is a non-removable discontinuity at x is equal to 0. Okay, let's look at this one over here. What can we say about that one? It is discontinuous, that's right. And it has a hole at x is equal to 1. Okay. How about this next one? Is that continuous? Looks like it, doesn't it? Doesn't look like there's no asymptotes, there's no holes, right? There's no jumps, no asymptotes, holes, or jumps. So this one is continuous. It is piecewise. You'll notice it is a piecewise function, but at the point where part of it doesn't exist, the other part does exist at that exact point. We're going to be finding out what that exact point is in just a minute. But it's continuous, right? I don't have to pick my pencil up to draw the whole thing. Okay. How about this one here? Is this continuous or not? Yeah, that one's continuous for all real numbers, right? Okay. Now, if we're looking at this, let's get a little bit more detailed about this, right? So we can see that we have an open interval, right? So if I have an interval where the endpoints are not contained, correct? So the endpoints are not contained on the interval. And I may have added this one too because I liked it. Yeah. So we want to know on this open interval, we want to, at each point of discontinuity, state the condition that it is violating, right? So why is it discontinuous at that point? So if I'm looking here and I'm tracing along, I have a hole that happens at 1, correct? So this would be discontinuous at x is equal to 1. And what can we say about that? We have a hole, right? In other words, we have a removable discontinuity. Now, if we go back and we're talking about the properties that we said, those 3 rules that we have to try to meet, okay? This function or this value at x, if I come to that point, does the function exist at 1? Is there a value of the function at 1? Yes,
Yes.
right? It exists, it's at 4. What is the limit as x approaches 1 of this function?
3.
That's right, because if I move this way, it's at 3. If I move from the right, it's at 3. So because these two are not equal, it violated that 3rd rule of our continuity properties. Okay, see what we're looking at here? So if I ask you a question like this on a test, that's the kind of information I would want to see. Where is it at? How does it violate the rules, right? It passed the first 2, but it doesn't, or it passed the, anyway, it explains it. All right, how about this next one? We have another discontinuity when x is equal to 2. What kind of a description would I give this one? It's a jump, right? Because we're jumping from one spot to the other, right? Does the function exist at 2?
Yes.
Yes, okay. And let's talk about the limit. The limit from the left as x approaches 2 is what?
2.
The limit as x approaches 2 from the right is what? Okay, so we have the left and the right limit as x approaches 2 of this function. In other words, it does not exist, does it? Because they are different. Because the left and the right limits are different, the limit at 2 doesn't exist, right? Okay. And then the last one that we have here is occurring when x is equal to 3. This is also a hole. It's a little bit different from the previous hole because the reason that would be kind of a removable hole is because I can replace the hole with what it is existed at, correct? That's how the difference looks there. Now, does the function exist at 3? No, so the function is undefined and therefore we don't even have to go any further because it doesn't meet that criteria. Okay? So that's what we mean when we're talking about being able to talk about the discontinuities and state the conditions that are violated, right? State why it didn't work. Okay. Now, how about if we look at this a little bit more algebraically without the graph, okay? So here, we want to know whether or not this polynomial f of x is equal to what you see there. I want to know whether the function is continuous at a if a is equal to 1. So f of 1 is equal to what? What happens when I plug in 1 for the function? It's undefined. And so according to what we just looked at above, is this continuous or not? No, because it's not, because the function is undefined. So therefore, 3 dots mean therefore we are not continuous or discontinuous, either one.
So we have to get a little 3 dot thing.
No, I'm just telling you, it's not, it's because it's not. Okay, therefore, how about that? Now, that's if we're talking about a being equal to 1. Let's look at that function again. And let's say, okay, well, let's move over. Let's talk about, is the function continuous when a is equal to 2? Same function. What is the value of the function when a is equal to 2? Well, that would be 3 times, it exists in the denominator, doesn't it? Okay, so then we're just gonna say, all right, plug it in, let's see what it gets. 3 times 2 squared plus 2 times 2 plus 1 over the denominator gives me 17. Okay? So just plugging it in, I find out that it's 17. So the function obviously exists at 2 because the value of the function is 17. The next thing we have to check is the limit of the function as x approaches 2 of this function. So if I thought about this, I could say, okay, well, the limit as x approaches 2 of the numerator, 3x squared plus 2x plus 1, over the limit as x approaches 2 of the denominator, still gives me the same 17 over 1, which is still 17, right? And the reason I did it this way is in case you're looking at anything else, right? Remember, we have a rational function here with a polynomial in the numerator and a polynomial in the denominator, so I could almost look at those as separate limits, right? Okay. 17 over 1. So is the value of the function the exact same as the limit of the function at that point? It is, right? Because these two things are equal, then we can say it is continuous. Algebraically. So we're just checking off, right? It's a checklist. We're just making sure that it exists. Now this last one is a little bit more involved. It's a piecewise function. It's a piecewise function. And so we're going to have to look at it in that aspect. So we have this function that's defined as x sine 1 over x when x is not equal to 0. And then it's equal to 0 when x is equal to 0. The function is equal to 0 when x is equal to 0. So moving through that checklist, the value of the function when a is equal to 0 is 0, right? That's what that piece of the function tells me. Correct? Okay. The value of the function when x is equal to 0 is equal to 0. Now, we have to look at the limit. So the limit as x approaches 0 of this function, if I use of h of x, if I use direct substitution, what am I going to end up with here? Undefined, right? Because I can't have a 0 in the denominator. All right, so let's go over here really fast and let's use our newfound squeeze theorem. Okay, let's look at this for just a second using the squeeze theorem. So if I just look at this portion, and I say sine of 1 over x. Well, if you go graph sine of 1 over x, you'll find that that function oscillates. Remember, it had a bunch of noise right around the origin. Okay, so if you were to graph that, you'll see that it's going to get really, really oscillating right at 0, but then it'll kind of even itself out. But it bounces back and forth between negative and positive 1. So if I can kind of use the squeeze theorem and prove a limit exists at in its boundaries, right, on its left and right side, then I've also proved the limit of the inside function, right? That's the squeeze theorem. So we're doing the same concept as we did before. Okay, so if I know that sine x exists between negative and positive 1, and then I come in here and I again multiply everything in there by x because I need x sine x, right? I need to find the limit of x sine x. So I would have negative x less than or equal to x sine 1 over x, which has got to be less than or equal to x. All right, so we're looking for the limit as x approaches 0. The limit as x approaches 0 of negative x is 0. The limit as x approaches 0 of x is 0. Therefore, the limit as x approaches 0 of x sine 1 over x has to be equal to what? 0. Okay? So moving back up here, the limit of the function as x approaches 0 is 0. So is the value of the function and the limit of the function the same number? And therefore this would be continuous by the squeeze theorem. Okay, now I chose the sign of the sign of 1 over x to give the boundaries, and then I just multiplied everything in there by what I needed, right? That's how I was using that. All right, the last thing we're going to do, because this will kind of finish us up here for today. So this is basically the same type of question we were just looking at, only it's just asking it a little bit differently. I want to know what are the values of the function that make it not continuous, right? So things that make you not continuous are holes and asymptotes and jumps, but mainly holes and asymptotes is what we're thinking, right? So if I have the function f of x is equal to 4 over x minus 6, how is this function discontinuous? Does it have a hole or is it undefined? Does it have an asymptote anywhere? How do we know where the asymptote's at? What can I find? All right, so I'm going to take the denominator, set it equal to 0, and I know that when x is equal to 6, the function is undefined. In other words, the function has an asymptote, doesn't it? Remember what it looks like when we have a hole. The hole is when our factor canceled, right? Asymptotes are where the denominator is undefined. So we have an asymptote, and therefore we have discontinuity at x is equal to 6. That's the x value at which point this is discontinuous. Let's think about the next one, cosine of pi over 2. Cosine of pi over 2x, right? Pi over 2 is simply the period, right? It tells me how many pictures I'm going to see in one period. But cosine's continuous, isn't it? We don't have any holes, we don't have any asymptotes, we don't have any jumps, do we? It's just one squiggle line that's continuous. I can trace my pencil over it the entire way, right? Okay, so just what I know about cosine, I can tell you that this function is continuous for all real numbers. The double line with an R is the set notation for all real numbers. Most of the time, your transcendentals are going to be continuous, right? Polynomials. Most of the time, our polynomials, weren't those our 4th and 5th and 6th degree polynomials? Aren't those just variations of like a W, like field goal, goalposts and Egyptians, right? It's all the same, okay? Natural log or exponential functions are continuous, right? Log functions are continuous. Sine functions, all of our trig functions are actually continuous on their domain. That's kind of another one to think about, right? On their domain. So wherever they are defined at, even though they have those asymptotes, as long as they're defined, and if that's the section we're looking at, it would be continuous on that domain. Okay, and we'll get a little further into that in a few minutes, or tomorrow. We'll pick up with this lecture and talk about infinite and some other limits when we come back. Practice the homework and ask some questions when you get back here next tomorrow. Infinite limits